right. So, in this the second practical exercise, you were supposed to work on a scanner using the Lex scanner generator. And we had a number of tasks, which turned out to be more complex, considering the background we were assuming, than we initially thought. So let's see what you had to do. So the whole question was revolving around building a clone of a typical Unix tool using the Lex scanner generator. And the Unix tool you were supposed to build a clone of was the WC or word count tool. And the question we stated, or the exercise text, was stating the following: that the Unix word count tool outputs the following information about a given text file: the number of lines in the file, the number of words in the file, and the number of characters in the file. Now that's exactly what word count does. The problem is the definition of words and lines, for example. So we stated that words are separated by white space or punctuation. WC on Unix sees it a bit differently. The question was, well, what could you do about it, or what were the problems here? So first, the confusion was that the real word count on Unix only uses white space as separators. So the question is, of course, what exactly is a white space character? And another problem was the treatment of the last line of a file. So counting the number of lines in a file, we didn't really define what is a line in a file. So let's take a look at these points first. So white space only uses, word count only uses white space as separators, and our question asked to also use punctuation characters, which we didn't really specify. So obviously we won't be very strict in grading this, so we accept solutions that only use white space. We'll also accept solutions that use any sensible definition of punctuation. This was especially problematic for one of the test cases we provided, test case A5, because this contained an apostrophe, so there's represented as an ASCII single quote character in the word don't, and dots, as well as an @ sign in this email address, testmail@domain.dom. So when you followed our recommendation in the question, you got a different result to word count. And of course, that's our fault. So we will simply accept, well, any sensible solution to this. So word count only uses white space as separators. So what exactly is white space? Now here we again dig a bit into Unix history. So if you read the word count man page, and I took this excerpt from the macOS man page here on my machine, it says white space characters are the set of characters for which the isW space libc, so in section 3 of the manual, function returns true. Now, if you look up this isW space libc function, this is described as a function for white characters, which are usually 16-bit based Unicode characters. And we will only be concerned with ASCII characters here. So that cannot work for our case here. And I actually think that's not correct in the man page, even though Linux says something similar, but I don't know who copied from whom. And again, I know that many macOS man pages are in pretty bad shape, so they're incorrect or no longer up to date. I have complained about this like already in 2003, and nothing has changed. So I'm not hoping for much positive change here. Now, what helps for our situation here is that there is also a function called simply is_space in libc. And if you call the is_space man page without the W, it says the is_space function tests for the white space characters. For any locale, this includes the following standard characters, and then there's a listing of the escape characters we would use in a printf format string. So \t stands for a tab character, so what happens when you push the tab key, obviously. \n is a new line character. \v is something strange called a vertical tab I've never seen in real life being used. \f is something which is called a form feed. Now, this is mostly used if you have a page-based printer. A form feed character would cause the printer to eject the current page and continue printing on the next one. And a carriage return, so you know there's two characters depending on your system indicating the end of the line. So Unix uses the new line character to indicate that the line is ending. Old macOS systems before macOS 10 used the return character here, and Windows is on the safe side, so they use both. So they use first a return and then a new line character to indicate that the line has ended. But anyways, it's whitespace because, well, whitespace, the name, of course, comes from the fact that all of these have some functionality, like on a printer, they would move the print head or eject some paper, but they don't print any character. So because you can't see a tab character or a new line character or something in print. And of course, the last character here, oops, sorry, shouldn't click it. The last character here is just a regular space character, which you get when hitting the space bar. Now, there's one word that might be confusing in this man page for any locale. What's a locale? Now, when Unix was invented, well, it was invented in the US, so nobody who worked on Unix actually thought this would be used in any other country. Like, yeah, so many problems that show up in America. Now, of course, Unix is used all over the world. So the standard locale, which is called the C locale, related to the language, is no longer sufficient because you have special characters. You have umlauts in German, or you have similar ones in Norwegian, and of course you have very different character sets like Japanese or Arabic or Chinese characters, and all of these should be supported. So it can be that some of these declarations of locales, so a character set plus conventions how to use them, includes additional characters that indicate white space. So if you have a Unix system that actually uses a different locale because, well, you're somewhere in Asia, for example, then it might happen that actually the word count function on that Unix actually accepts additional characters as white space. So that might be confusing. So we're currently restricting ourselves to these couple of characters here. So that's just an additional information if you were confused when reading the man page about what all this locale stuff means. Essentially, it's a big old hack because it extended a system that only, well, had the 26 characters of the standard ASCII alphabet plus uppercase and a few extra symbols and the digits, but that wouldn't really work with, well, any system outside of the English-speaking world. All right. So the final problem that showed up in discussions on Piazza was, what about the last line of a file? So some of you figured out that they entered a text in the editor which had like 5 lines in the editor. They saved it and they ran word count on it and maybe their own implementation, and they got a result of 4 lines. Now this has to do with the definition of a line in word count. So word count, again, the man page says a line is defined as a string of characters delimited by a new line character. Characters beyond the final new line character will not be included in the line count. Now, some editors, actually, when you write a text, do not automatically add a new line character. So in Unix, the \n or ASCII hexadecimal 0A character at the end of the last line of your text. So for example, Mac OS Text Edit is one of the tools that don't automatically add a new line characters. Whereas some other editors do this automatically. I tested it in Vim, and my files in Vim automatically had a new line appended to the last line of my text. So this is a difference, and if you have such an editor that doesn't automatically add a new line character to the last line of your text, well, then you get a count of 1 line fewer than you would expect when just counting the lines on the screen. So if you want to be consistent with word count, you would only have to count the new line characters, even if this would be inconsistent with the common sense, with your intuition, if you just count lines on a piece of paper or a screen. So that's a bit of a stupid definition. In addition, again, my complaints about Unix man pages, a line is defined as a string of characters delimited by new line. So a string of characters does this also allow a string of 0 characters? So would this mean a new line on its own, which indicates an empty line, would be counted as a line or not? That might be an additional question. It usually is counted as a line. So this string of characters, which the man page defines, can also be an empty string. But that's not obvious from the man page. So you can experiment with this using word count, and then you would find out it also counts empty lines. So how can we implement our Unix word count clone tool? Now, this is a very simple Lex parser. So what we do here, as we've seen before, in this percent curly bracket section here, we can include literal code that's literally copied into our generated C code. So we want to include our standard IO header because we want to print something later on. And we can declare some variables like variables to keep count of the number of lines, number of characters, and number of words. And we all initialize them to 0. Then we've seen we have this %%. This is the separator between the 3 sections of a Lex file. So in the second section here, we have our rules defining our DEA to detect our patterns here. And we've seen these rules are processed one after the other. So whenever a character comes in, it's first checked if it matches rule 1. If it matches rule 1, then the according action here is executed, and this is again just C code that's copied into the generated C code. If it doesn't match that one, the Lex generated scanner checks for the next rule here. If it matches that one, well, then it executes this one. And finally, we have this dot character here, which might be a bit hard to see. So this dot character always stands for any arbitrary input character. And since this is our last rule, this is a catch-all case. So if it doesn't match a new line, it doesn't match any of these characters here, it always matches this dot character here. And well, this ensures that you don't accidentally leave out a character. But of course, if you included this dot character as the first rule, then this would catch all characters, which means the other rules would never actually be evaluated. So if you have something like this, always take care of the order. Now, what are we doing as a rule here? So for \n for a new line, well, according to our definition, well, we increase the number of lines as soon as we see a new line character. And as new line is also a character in itself, we also increase the number of characters. Now here I've used for this first example a very strict definition of punctuation. So essentially in the original text we said that any punctuation character should be treated as a separator. So if you turn this condition around, any character that's not a punctuation character should be treated as part of a word. Now in this example we have included uppercase and lowercase characters, the digits, and I've also included a regular minus or dash character here. And because the dash character has this special meaning in a rule here to indicate a range, you need to prepend it with a backslash. So that's what we call escaping this character. So it doesn't have this special meaning of indicating a range anymore. So for this example here, we would count as words everything that hangs together and consists only of a sequence of one or more of these ASCII characters here. So capital and lowercase letters, digits 0 to 9, and a dash. Now, since we match one or more characters here, we cannot simply increase our character counts because this matching string here can be more than one character long. So what we do here is we increase the number of characters by the string length of YY text. So YY text always contains the token you've just detected in your automaton. And since you assumed that everything outside of this is a separator character here, then after you've read a consecutive sequence of these characters here, you know you've read another word, so you increase the number of words also. And finally, when you read any other character here, which is, well, by omission defined as a separating white space punctuation something character, you simply increase the number of characters. And so what's left to do is in main you call yylex, and yylex then automatically updates these variables here. So we've done something we usually don't recommend, using global variables here, but here they make our life quite a bit easier. So these global variables are updated by the running Lex scanner, and Lex finally returns, because we don't return from our scanner here, as you see. So it continues running, scanning characters. And it finally returns when there's no more characters in the input. So your file or your input is ended. So then you return from YYLex, and you can output your 3 counts you've updated. So the number of lines, words, and characters here. So if you want this alternative definition that's closer to what word count is doing in real life, you can write it like this. And I hope this works, because I only tested it on one file. I just thought I'd give you an alternative. So what you do here is essentially you flip this around and you explicitly now detect sequences of white space instead of sequences of word. And since you know white space separates words, you can increase the number of words when you see a sequence of white space, and you also increase the number of characters by the amount of white space characters you've just read. So any other character here, well, is a punctuation or alphabetic or digit character. So anything in our more precise definition that makes up a word. So here we just increase the number of characters, because now we count words not when we detected words, but when we detect the gap between words. So this is turning this around. This is a little trick that also works. To be honest, I haven't looked at the word count source code implementation. I don't think it's written in Lex. So they've used a handwritten scanner, I suppose. Might be interesting to take a look at how they actually implement this in real life word count code. So this would also be an alternative. And as I said, we're definitely not strict when grading this. So if your solution has any sensible definition of whatever splits words, we're fine with this, obviously. Okay, so this was the first part of it. The second part of the exercise, one more thing that came up before I talk about the second thing of the exercise. So some of you had problems linking the program, because when you use the provided makefile, it actually executes the stuff I've written here by hand. So first you call Lex on your Lex source file, which gives you the Lex YYC file, and then you compile it, and you have to link the Lex library using the -ll option here. Now on some systems, this -ll library is not available. So usually -ll means the linker is looking for a library called libl, which is the Lex library. Now, Linux systems usually have the Flex GNU alternative, which is a re-implementation of Lex by the GNU project. And by standard, the GNU library for the GNU Flex scanner generator is called libfl for libflex. And at least in earlier Linux systems, there was always a symbolic link to libl. So when you used libl -ll, it was automatically used. It seems that some systems don't do this anymore. So for these systems, you need to use -lfl to explicitly link the Flex library instead of the Lex library. That was a bit surprising, because I'm using Unix for 30 years and that hasn't happened to me before. But yeah, well, that shows I can also probably learn some stuff still. All right. Word count is really strange. So if you look at the macOS man page and read a bit further, it gives some historical information. So even the authors of word count weren't really sure what they should do. So the man page says, historically, the word count utility was documented to define a word as a maximal string of characters delimited by space, tab, or new line characters. So this was a very restrictive definition of white space. And it didn't say anything about line numbers. And then the man page continues. The implementation, however, did not handle non-printing characters correctly. So some of these characters, like every character you get when you press Control something on your keyboard, is a character with an ASCII code lower than 32, so in the space between 0 and 31. And if you type something like space, Control-E, D, Control-E, and space, this was counted as 6 space characters, so white space. Whereas when you included this inside of a string, this was counted as 8 characters. So this was quite confusing, and this has changed a bit like 20 years ago to modify the implementation to be consistent with the documentation. So even back then, the people who had to write the documentation were not the ones who implemented this. You probably know this: when you write a program, you don't really want to write additional documentation, and that was the case like 20 years ago also. So then again, they refer to is whitespace again, and to a Unix standard, POSIX standard. So I think it's fine to be a bit confused about the word count behavior. And you see, we were also a bit confused about this. So we'll probably think of a different exercise for next year. So sorry for the confusion this has caused. But anyways, this has caused some interesting discussions. So I think it was still hopefully not a too frustrating experience. So finally, going to 2.2, you were expected to extend the word count tool you wrote to also count the number of strings. So strings are delimited by the double quote ASCII character, and to output the average string length. And we said that you may assume that a string never extends beyond the end of a line. Well, of course, one of our test cases, B1, had strings that extended beyond the end of a line. Ouch. So what are your options there? So either you believe us, so you believe what we write, and don't count strings that actually span 2 lines or more lines as strings. So any line with an odd number of double quotes, well, you have to ignore the last double quote, obviously, because an even number of double quotes always includes a string when it's on a line. Or you could also choose not to trust us and count the strings nevertheless, even if they exceeded beyond a new line. I don't mind. So we'll accept both solutions, obviously, because yeah, that was a bit stupid from our side to do it that way. Anyways, how can you do this? So the challenge here, if you want to count strings, is that you need to keep a state. Oops, there's something left from my editing here. Sorry. So what we do here is we extend our lex scanner a bit. So in the first section, we add a counter for the number of strings and also for our string length. And what we do now is we actually define a new state. So a state means we partition our automaton that's generated in different parts between which we can explicitly switch. So the part we're in initially is called, surprisingly, initial. So that means when we put something in this angle brackets here with a name of a state, and initial is automatically defined, if we put this in front of such a regular expression pattern, this means we have to be in state initial in order for this to be detected. And accordingly, if we put string, so the state we defined up here, in front of a set of characters, so a regular expression, then we need to be in string. So we need to have a functionality to switch between the different states of our scanner. And well, we do this using this begin macro. So this is a macro actually defined by Lex, and this is stuff supported by the Lex library. And begin says we're switching to this different mode of our automaton to scan. So whenever we are in the initial state and detect a double quote, we need to escape this again. So to indicate that this doesn't have a special meaning, then we know we've found the start of a string. Because if we were already in a string, we wouldn't be in our initial state. So what we do here, if we encounter a double quote character, we increase the number of characters, obviously, and then tell our Lex scanner that we want to switch to our string state. So when we're in our string state, especially that one here is ignored. So in our string state, when we encounter a double quote, what we do is we also increase the number of characters. And now we know we are in the string state. So we've already seen this initial double quote character, the opening one, and also the closing one now by matching that one here. So we know we've seen an additional string, and we're now outside of a string again. So we go back to our initial state. And otherwise, when we're in string and match any arbitrary character, we increase the overall number of characters and we increase the string length. And finally, when we match any arbitrary character, so the fall through case, we just increase the number of characters here. So what's important here is that we actually now keep count of a string length. So for each character inside of a set of matched double quotes here, no matter what it is, we just increase this variable here. And what's important is, since we also should print the average length of a string, that we also keep track of the number of strings that we encountered here. So whenever we see a closing double quote that has matched an opening double quote automatically because of our states, we also increase the number of strings. So when we want to print this, well, we use our yylex function again and print our regular output. Then we print the number of strings using the global variable we've used for that. And then if we have any strings, because we want to avoid a division by 0 here, we can also print the average string length simply as the accumulated length of all characters, so the sum of the number of all characters of the string, so how many characters do we have all together in all of our strings, divided by the number of strings. Now, if you look closely, you'll see this solution also works somewhat with strings that actually extend beyond the end of the line. But since we are matching a new line character here in the previous slide, without any state qualifiers, new line characters are not included in string length calculations. So we would have an incorrect string length. So this solution still lacks some details. Still, we would count it as a correct solution here. So if you explicitly want to exclude the case of strings to extend beyond the end of a line, you would need to switch from string back to initial when matching new line also. So in this case, when there's a new line, you would somehow need to switch back. So you'd never see this closing string character, so you wouldn't increase the number of strings. That should probably work. It might still cause problems with the string lengths you accumulate. So you'd have to use some additional code there. So as I said, it's actually not that simple getting word count right, especially not if you use our proposals for extensions. But anyways, we're not that strict, so we'll accept this if it sounds reasonable. Okay, so finally, we had some test cases here. And you've seen that there were several unclear cases which didn't really match what the exercise said. This was not intended. We didn't want to trick you with this, obviously. Well, we need to do some quality assurance and maybe some more testing. So sorry for being our guinea pigs for this exercise. So obviously, if some of the test cases don't exactly return the correct result for the exercise, it's okay as long as they don't return complete garbage here. So I won't complain about that. So I hope still this was an interesting introduction into working with Lex with simple examples. And what's interesting, I don't know if any one of you have tried to implement word count as a C program. So you see, by having this scanner generator automatically generate all the automaton stuff, you save a lot of work, even if you have to invest quite some work to get it right. Because writing such a word count tool by hand in C takes quite a bit more time, I think, to get it right. Would be interesting to have a comparison here. I didn't try. You could, of course, look at the Unix word count source code, but since Unix has grown quite big, I think this would be a bit too complex for minimal functionality here. So yeah, we won't discuss this here because, well, that's probably a waste of time, because ultimately we, of course, want to use our scanner in order to build a part of our compiler later on. So the next exercises will be concerned with building parts of our compiler for a simple language, which we are going to use throughout the rest of our course. So that's all from my side for today. Thanks for listening, and I'll